All right, Clinton, do you want to start now?
Sure. Okay. Hi, my name is Clinton Pan.
Hi, I'm Kieran Koda, and me and Clinton, we founded this society about 4 or 5 months ago. And we're very excited to have our very first speaker in the society. Also first, before we go over that, thank you for coming out to a lecture. This is a really cool thing just to meet everyone and just a geek out about astronomy. With us today, we're very excited to have Dr. Kirkpatrick from Caltech IPAC.
So, Dr. Kirkpatrick is a leading researcher in the field of brown dwarfs, low-mass stars, and optical telescopes. He has a wide list of groundbreaking discoveries and accomplishments during his astronomy career. To name a few, he established the L, T, and Y spectral classes for brown dwarfs. Furthermore, he has won many awards, including having his research being named as one of the top 10 science discoveries of the W.M. Keck Observatory.
And one thing before we start, at the very end of the lecture, we'll have like a time to ask questions. So if you have any questions throughout the lecture, just write it down in the chat or like a piece of paper, and then at the very end we can have a time for like questions. And yeah, and then without further ado, let's welcome Dr. Kirkpatrick.
Okay, thanks everybody. See if I can get the presentation to work here. Okay. Okay, can everyone see that okay?
Yep.
Okay, and can you also see my cursor when I move it?
Are you moving it right now?
Yeah.
No.
Okay, all right, well, we'll have to wing that then.
All right.
Okay, so thank you for that introduction. I am Davy Kirkpatrick. I'm at the California Institute of Technology, and I'm a lead research astronomer there. And I'm going to give you a little talk today about not only how I got into astronomy, because Tarun wanted me to give you some background on how I ventured into this field, and also what it is I study in astronomy. So the overview of the talk is actually pretty simple. I'm just going to spend the first third, again, talking about why I chose astronomy as a field of study, and then why I went into brown dwarfs specifically, and then what my team finally is doing in brown dwarf research. Okay, so this is how I chose astronomy. So I grew up in the southeastern United States in a little town called Hendersonville, Tennessee, which is not too far from Nashville. And I grew up on a dairy and tobacco farm there. And the two photos there on the left are just photos of me when I was a little kid in amongst the Holstein calves, and also that's at the top. And down at the bottom, me amongst the tobacco patch with a glass of water in my hand because it was very hot that day. And I lived on a property where we had a lot of roaming fields and things. We had hills, we had creeks. You know, there was pasture land for the cows. There was clearly tilled land for the tobacco and things like that. And we also had vegetable gardens. But between chores, we had a lot of fun just roaming around and seeing what nature was like. And the photo there at the bottom is just showing me on the far right with my two brothers. And that was my brother's prize-winning pumpkin that year. So we had a lot of times between chores just go out exploring. And at an early age, somehow I just became interested in science. And I can't really tell you why. I was just kind of a curious child, I guess. But one of the things that my younger brother and I liked to find a lot was we'd go down to the creek and pull out these funny-looking rocks. And we found out with a little bit of research that these funny-looking rocks that we were finding were actually fossilized animals and plants from hundreds of millions of years ago. And these are photos of a few of the fossils we found at the creek on our farm. The top one is just a piece of a single coral. The one in the top right is something called a crinoid, which is also known as a sea lily from hundreds of millions of years ago.
Sorry for interrupting, but
Sure.
I don't think we can see the presentation moving.
Oh, is it stuck?
Yeah.
Aha, okay.
Yeah. And maybe try like reset mode or something like that of some sort. Maybe that's why we can't see it moving.
Let's see. I put it. Let me do this a different way then.
All right.
I will try to start the slideshow from this. Okay, now I'm advancing to the first slide that's got overview of talk. Can you see that?
No, we still see the rock, the coral rocks.
Oh, okay.
So actually, I think it's working. I think it's just lagging a little bit because now we see the overview of talk, and then you just move back to the rock thing.
Okay. So there's just a time lag then. Okay.
Yeah, I mean, that's fine, I guess.
Okay, so let me go back to the full screen mode. So are you seeing the rocks again now?
Yes.
Yeah.
Okay, so what I'll do is I'll just pause after I do an advance to the next slide, and you can tell me if you're seeing it or not.
Wait, so maybe before you go into that, so right now we're not seeing it in full screen mode. We're just seeing it in normal mode. So maybe the problem was full screen mode.
Oh, okay. So if I keep it like that, maybe that's better.
Yeah, I think that's probably the best.
Okay, all right. Well, technical details. Okay, did you guys see the other slides? So are we, you saw this one?
Yep.
Okay, with my brothers and me, and now you saw the one here with the rocks.
Yep.
Okay, great. So in addition to the sea lily that's in the upper right, we also found things like the shell at the lower left, something called a bryozoan, which is there in the middle, and then on the lower right, something called a cephalopod, which is just the same family of creatures that the squid is in, for example. So these are all items that came from the sea back when Tennessee used to be underwater hundreds of millions of years ago. Well, the other thing we would do and this is with both of my brothers this time, and you're all seeing the new slide with the arrowheads on it?
Yep.
Okay. And these are some arrowheads we found, and also some flint scrapers and things that we found on the farm. And these are really easy to find when we would have tilled land. And if a strong rain came and sort of washed off the rocks that had been thrown up in the tilling of the soil, you could very easily spot these arrowheads that would just pop out. And of course, these are arrowheads that were made by the Native Americans who lived in the region that we then inhabited later. And it was kind of fun to find all these things and wonder what they were used for, because some were clearly, spear points, and other ones were probably scrapers they used on animal pelts or something. But it was kind of fun to find all this stuff and wonder how long ago it was made and what it was actually used for. Okay, and then next, this is another science interest of mine. So there were times in the fall when it would start to get cold, that my dad would go up to one of our pieces of property called the Old Field, and he would take all of the downed branches from the trees and pile them all up in one giant pile just to get rid of them. And he decided one year that, why don't all the extended family hop on a hay wagon one night, drive up to the Old Field, and we'd all set the pile of wood on fire, and we would do things like roast hot dogs and marshmallows and things like that, and just have a good time. And this became an annual tradition. We would do this every fall. And there was one of those years when I was a kid, when we were coming back after it was all over, and I was lying back on the hay wagon looking up at the night sky, and I just became fascinated by all the stars that were up there. And this is just a photo of one of the bonfires we had lit. And in the lower left, you can see behind my two aunts, you can see the actual hay wagon in the background. The hay wagon is stacked with hot dogs and casseroles and chili and drinks and things like that. So we all had a good time doing this. Well, it was after that experience, one day I decided to ask my dad what some of those things up in the sky were called, because I became very, very curious what I was looking at. And my dad, who's shown here on the left with me, was an avid sky watcher himself, and you can see he's got a pair of binoculars around his neck there. And he could tell me which objects were the planets, because he knew the planets moved in relation to the background stars, but he couldn't tell me which planet was which. And he didn't know what any of the stars were called. And I was just very frustrated. I'm like, I need to know more. I'm really interested in the night sky, and I want to know what's up there. But he didn't know, and I just had to go for a couple of years not knowing what those things up there were. And then one day I had my epiphany. And my epiphany came about when in my elementary school, we were finally introduced to the elementary school library and what the Dewey Decimal System was and all that kind of fun stuff. And I remember after the librarian gave us an introduction to the Dewey Decimal System, I ran over to the card catalog and looked up astronomy right away. And I figured out where in the library the astronomy books were. So I ran over to the astronomy section, and I found a few books there that were just very advanced. They had big, long words in them, and there weren't very many pictures. And I was like, oh my, I'm never going to learn anything about this. But in amongst all those thick textbooks, I found these two narrow little textbooks, which are shown here, called Find the Constellations and the Stars, A New Way to See Them, by an author known as H.A. Rey. And some of you may know H.A. Rey from his other works, because he's most famous for writing a bunch of children's books on Curious George, who's the curious chimpanzee who was always getting into various adventures and things and getting himself in trouble. But H.A. Rey had also written a couple of books about finding the constellations and figuring out what the star names were and stuff like that. And I was just hooked. I thought this was so cool. I could finally figure out what I was looking at. So it wasn't long after that I started thinking about what I wanted to do with my life. And I was kind of early on wondering about this as a kid. But I decided I wanted to be in some sort of science field because I really, really like science. But I started to clump together things like the fossils and the arrowheads I was finding into things that were remnants of the past. And I started looking at astronomy as where we might go as a civilization in the future. And I decided that I really wanted to be more forward-looking than looking backward. So I decided rather than study either, paleontology or something, or early cultures, I would go into astronomy instead. So that's what I decided to do. And I actually have a little bit of proof of when I made that decision, because my mom had given me this school year's little spiral binder that had a two-sided page for each grade. So first grade, second grade, third grade, and so forth. And on the back side of each page, it had things like who your new friends are and what your activities were. But there was a section there towards the bottom where it says, what do you want to be when you grow up? And by the fifth grade, I had written down astronomer. I didn't know how to spell it yet, but I knew I wanted to be an astronomer by the fifth grade. And now that I look back at this notebook, I realized that in the first through fourth grades, I was writing stuff like policeman and fireman and farmer and things like that. But after the fifth grade, every single entry after that said astronomer. So I knew that's what I wanted to be. Okay, so I'm going to move on now and tell you a little bit about what brown dwarfs are, which is the field I study. Okay, so let's make sure that these are going to work. Yeah, it looks like they will. Okay, so brown dwarfs are objects that form like stars do. So there'll be a cloud of collapsing gas that starts to fall in via its own gravitational pull. And that gravitational pull will start to form clumps in it because it's not a continuous, just straight down collapse into a single object, because there's going to be inhomogeneities in the gas clumpiness. So it's not going to collapse into a single ball. But I'll just show you some simulations of here of two different kinds of gas of different mixtures of chemicals to show you exactly what they do based on the physics when they start to collapse gravitationally. And each one of these shows you a frame about every 1,000 years. So this is greatly sped up from what you would actually see in the sky, of course. But you'll see these clumps, and the animation will stop for a few minutes and then rotate so you can see a more interesting part of the cloud to see what's going on. But those brighter areas in the middle are where the clumps are becoming more and more dense, and you're starting to form stars there. And you'll see in the one on the left, you've got a binary system that's very rapidly rotating around. So you've got two stars that have formed there, and they start to interact with other stars there on the left that have already formed. And you'll see some of them get slung out just from the gravitational slingshot effect. And over on the right, you see some of the same stuff is happening. So this is what we think happens when a cloud of gas starts to collapse and form stars. Well, there's, based on these theoretical predictions, back in 1963, there were a series of theorists named Kumar and also Hayashi and Nakano, who said, there's a point at which star formation can form something that is so small and less massive that it will not be able to burn thermonuclear fusion in its core. which means it won't be shining for billions of years the way a star does. So after it has collapsed into its final form, you won't have an internal energy source, and it will just continue to cool and cool and cool with time. But that was something that had never been seen before, and it was just a theory. No one knew if these things actually existed. In fact, people didn't even know how far down the star formation process could produce objects. It could be that it only produced stars and didn't get to the point where things as low in mass as these other objects would even develop. Okay, now I'm going to show you what is a somewhat complicated diagram, and you're going to see this one a couple of times here, but I'm going to try to go through it and show you what this is actually describing. So this is just a plot that on the x-axis is showing age. So as you go all the way over to the right, we're talking about an age that's about several billion, tens of billions of years old, which is older than the universe actually is. So, and on the far left is times of essentially zero. This is a logarithmic scale, so you've got times where the x-axis says 1, that's actually 10 billion years. Where it says 0 is a billion years. Where it says -1 is 100 million years, and where it says -2 is 10 million years. So that's the kind of scale you're looking at here. And on the y-axis, we have the temperature of the object, and this is in Kelvin. So this is just showing you hotter objects on the top part of the diagram, and then very, very cold objects on the bottom reaching absolute zero. And the various colored lines that are shown on this diagram are objects that have formed from the star formation process of various masses. And the very top orange, I guess I should say orange, it's actually a golden, sort of a yellow track, has a tiny little number there on the upper right, which is, you probably can't see it very well, it's 0.100, and that's telling you what the mass is in terms of solar mass. So that's something that has 1/10 the mass of the sun. And for something that's 1/10 the mass of the sun, it forms way over in the upper left at a temperature of about 3200 Kelvin. And as it ages, as you move over to the left in the diagram, or I'm sorry, to the right in the diagram, you see that it maintains an almost constant temperature. There's a little bit of dip there about halfway through the track, and then it finally settles down, and it's a very, very constant. And what's happening in that little dip is it was very slowly cooling off, and then suddenly as it was collapsing, it reached an equilibrium configuration where the thermonuclear fusion in the core started to ignite. And then that ignition and the energy coming out started to balance the gravitational collapse. So now the star is stable. It's got an internal energy source that's burning for billions of years, and it will stay at that same temperature for tens to hundreds of billions of years. So it's got an internal energy source that has lots of fuel, and it will burn that way for a very long time. And everything that is shown there in the yellow curves, so you're going from 1/10 of a solar mass down to 9/10 of a solar mass, et cetera. 0.09 of a solar mass, I should say, and further down. All of those objects become stars because you see that all the yellow curves flatten out towards the far right. When you get down below about 72, or I should say 0.072 times the mass of the sun, which is about 72 Jupiter masses, if you want to put it in Jupiter units, you get those purple curves. And the purple curves you see never actually flatten out. And the reason they never flatten out is that you never get that internal nuclear fusion going in the core. So even after the object has reached its final equilibrium configuration, it continues to cool and cool and cool with time. So there's no stability there. It just continues to get darker and darker and darker. And there's a little inflection point on each one of the purple curves that is an indication of a very brief period called heavy hydrogen or deuterium burning, where the star starts to have a little bit of internal energy source, but then the fuel runs out because there's not very much heavy hydrogen in a star. And that's the only thing that distinguishes that from just cooling down continuously forever, which is what the objects in the very lower left part of the diagram, which is shown as cyan, does. So that's an object that's about 10 Jupiter masses, and you see it just cools forever. I mean, there's no inflection point to speak of at all. Okay, so let me move on. Now let me actually back up just a second. So if we look at those masses down there in the lower right-hand corner, I said they were getting down to, at least on this theoretical diagram, down to about 10 Jupiter masses themselves. And we're still talking about the star formation process, but it turns out that we think they're objects that form via the other process, which is the protoplanetary disk process, which creates planets that could also be as high or even higher than 10 Jupiter masses. So we have two different processes that are creating planet-like objects in the universe. So there's the star formation process and there's the planetary formation process. And the next slide shows just an example of the planetary formation process. So as I said in the previous slide, we have brown dwarfs being lower in mass than about 72 times the mass of Jupiter. And the theory tells us they can probably go down to about 7 times the mass of Jupiter, or maybe even lower if you sort of tweak the conditions in a certain way. But of course, there are objects that form out of a protoplanetary disk that form planets as well. And this is a secondary process because the star, which is shown here in the center of the simulation, has already formed and it's got leftover material around it. And that leftover material, as it starts to orbit the star, will start to clump up and it'll have its own gravitational instabilities. And it will start to form little clumps that then begin to gather their own material around them. And you'll see those little dots that are now circling the star are the planetesimals, the sort of the embryos of planets that will now start to form around that star. Okay, so this is kind of curious because now we have brown dwarfs that are formed like stars, but they're the same size and the same mass as things that form like exoplanets. So brown dwarfs kind of straddle two worlds. They're both a star in that the fact that they form like a star, but they're planet-like in that they have the same temperatures and the same masses as planets that are formed via the other process. And the thing that's kind of neat about brown dwarfs is they're primarily wandering alone out there by themselves in space, and they're a lot easier to follow up than your typical exoplanet, which is very often lost in the host of the bright star that it's circling around. So the brown dwarfs are just a lot easier to scrutinize. Okay, so we're going to look back at this diagram again. I hope this isn't too complicated. But the brown dwarfs we're looking at actually come in 4 different flavors. They're called M dwarfs, L dwarfs, T dwarfs, and Y dwarfs. And that's going from hottest to coldest. And I've put the little boxes here where they belong in that diagram that we talked about earlier. And if you look at the zone that has the M dwarfs in it, which is shown over here on the far left, so it's around 3000 Kelvin, you see the M dwarfs contain both real stars, which are the yellow curves on the far right, as well as brown dwarfs, which are the purple curves. But the older objects are the ones that are the stars, because they're to the right, and the younger objects, which are the purple ones, are the ones that are brown dwarfs. So you have M dwarfs can be either brown dwarfs or stars depending upon their age and their mass. As we go down to the next group, which is the L dwarfs around 2000 degrees, you can see it's the same thing, but now things have been shifted a little bit older. So only the very, very old objects that are L dwarfs are actually stars, and most of the L dwarfs that are left, the purple curves again, are brown dwarfs. If you go down even colder to the 1000 degree bin there, where you have the T dwarfs, you see everything is purple or even cyan. That means everything that's a T dwarf is a brown dwarf. There's absolutely nothing down there that can be a star anymore because they're just too cold. And as we go down even one more step to the ones that are closer to 0 Kelvin, those are the Y dwarfs. And they are just very, very cold, low mass brown dwarfs. Okay, so we'll go to the next slide. And the next slide is just showing wavelength versus the amount of light that comes out of the object itself. So these are actually spectra of various kinds of stars. Again, they're going to be the 4 spectral types we talked about a minute ago: M dwarfs, L dwarfs, T dwarfs, and Y dwarfs. And let me just explain what the axes are again. So the x-axis is showing the wavelength in something called microns. And at the far left, we have 0.6, and that corresponds to 0.6 microns, which is the same thing as 6,000 angstroms or 600 nanometers. And that's about the longest wavelength of light that the human eye can see. So everything on this diagram is what we call either the near infrared or the mid infrared. And these are all longer wavelengths than what your eye can detect. But you actually can feel that on your skin as sort of heat energy. And each one of these squiggly curves on here is what the light output of each one of these objects looks like. And the y-axis is on a logarithmic scale, and that means that if you go from the top spectrum, which is a mid-M dwarf, down to the bottom spectrum, which is an early Y dwarf, that's a difference in flux of about 1,000,000 times. So that means the M dwarf is about 1,000,000 times brighter than the Y dwarf, which means Y dwarfs are a lot harder to detect. But I just wanted to quickly show you what some of the funny looking chemicals are in the atmospheres of these objects, because you can see those as absorption bands in the actual light output. So the M dwarf has some familiar things in it, like H2O, which is just water, of course, and it's got CO, which is carbon monoxide. And there's also something which you may not have heard of called titanium oxide, because it's not something you find easily on Earth. But you see the titanium oxide on the far left is really chopping up the spectrum. There's those atoms in the atmosphere are actually absorbing light, and the light is kind of having a hard time getting out of that part of the atmosphere because it's this overlying titanium oxide absorption on it. Well, as you cool down from the mid-M dwarfs down to the next level, which is the mid-L dwarfs, you see a lot of the same kind of chemicals in the atmosphere, molecules like water, and now you have methane, CH4. You still have carbon monoxide, but you have a few other things that are hydrides like chromium hydride and iron hydride. And notice that the spectrum is beginning to look even bumpier because there's more absorption bands coming in, and the light is having a harder time finding its way out because there's molecules and atoms still absorbing them. As we cool down even more to the mid-T dwarfs, you see the spectrum is getting even more interesting. And we even have the first appearance of something called NH3 on the far right, which is ammonia. And we see ammonia in the planets of our solar system, for example. And then we go all the way down to the very coldest one, which is the early Y dwarf. You see the spectrum is just crazy because it's just up and down and up and down and up and down. And that's because it's got all kinds of molecular absorption on top of it. It's got water, it's got methane, it's got ammonia. And those are the kinds of things we would like to find. And in fact, that the methane, ammonia, and water absorption is very much like what you would see in a planet, like a giant planet of our solar system. Okay, so the last part of the talk, I'm just going to give you a feel for why my team decided to study brown dwarfs and what part of the brown dwarf research world we're actually quickly once again. So what we're trying to do in our current research is figure out how low in mass the star formation process can actually produce something. And we're looking down here at the right-hand part of the diagram where we see that cyan curve coming down, which is sort of 10 Jupiter masses. And what we're trying to do is find more of these very, very cold brown dwarfs called the Y dwarfs, see if we can discern from the number of those that are made how low in mass they actually are and how low down in mass the star formation process can actually produce things. So back in the late 1990s, we started thinking about this issue, and we started proposing a satellite mission to NASA called WISE, and WISE stands for the Wide Field Infrared Survey Explorer. There's a little schematic diagram of it shown there on the left. And we finally convinced NASA to start building it in the early 2000s. And we finally got it launched in December of 2009, and that's a photo of it going up on its rocket from Vandenberg Air Force Base here in California. It was very exciting to see this go up, because this was going to be our brown dwarf discovery engine, because these things, again, are very, very faint, and we needed a mission to actually go that deeply to find these objects. Okay, so let me tell you just a little bit about how the WISE spacecraft operates. So WISE was launched into an Earth orbit, and it goes over each one of the poles of the Earth. It takes about 90 minutes to go all the way around the Earth. And in this first little movie, you'll just see the spacecraft going around the Earth, around and around and around. And it's pointing outward towards the night sky at 90 degrees away from the sun. And it's basically following what we call the terminator, which is the the line that divides day and night on the Earth, because that's where you'd be 9 degrees away from the sun. And as we do that, and we keep taking data continuously as the satellite goes around the Earth, in this next diagram, you'll see that in 6 months, try that again. In 6 months, that little blue orbital plane there comes back in the same configuration it started with. So that means that if your satellite is looking out continuously like that as the Earth is orbiting the sun, in 6 months it will have swept out the entire sky. And I'll show you another little schematic for how that works. So, this one may not work. Let me see if I can go to this mode. Can you guys see this playing now?
I don't think we can see it.
Okay, all right. We'll not worry about that one then. So this was just showing that as the Earth orbits the sun in 6 months, you slowly get an entire map of the whole celestial sphere as WISE keeps observing. And I apologize that you can't see that one. Okay, so building a spacecraft for NASA is kind of like inventing your own little alien, and you can put any kind of arms and eyes and whatever you want on it, so it can see and feel and do whatever you want it to out there in space. And what we decided to do for WISE was to give it actually 4 eyes, not 3 eyes like the alien from Toy Story here. But 2 of those eyes were specifically designed to help us find brown dwarfs. And each one of those eyes could look at a different wavelength of light. And the shortest wavelength band, or the shortest wavelength eye, if you want to think of it as a little alien that we picked, was the one shown there in sort of the greenish blue color, which we call W1. And we selected that wavelength to be particular for very cold brown dwarfs, because if you look very carefully at the white dwarf spectrum there at the bottom, there's a very deep methane absorption band there, which means there's not a lot of light coming out in a brown dwarf at that particular wavelength. So brown dwarfs should be really, really difficult to detect in that wavelength. So you may be asking yourself, if they're so difficult to detect, why did you pick that as a band? That's a silly eye to pick if your eye can't even see it. But the idea was that if we picked the second eye, the second detector, to be around 4 or 5 microns, which was where you see that peak in the wide dwarf spectrum there at the bottom, then you've got one eye that can see the very cold brown dwarf really well, and you have the other eye that can't see it well at all. But if you combine those 2 data sets together, your eye might register that as a red, not a blue object, because most of the light is coming out at a longer wavelength. And this is the whole idea behind trying to find cold brown dwarfs in WISE, is that if we put those images together, like your eye might be able to see them if you were an alien, you could actually pick those out easily. And here's an example of this on the left, where we have an image of the sky that we flipped, so that instead of looking at white stars on a black background, you have black stars on kind of a white background. And we picked a color stretch so that things that are really, really bright in that second band, which we call W2, and very, very faint in the first band, which we call W1, pop out as orange. And this image in the upper left shows that there's one very, very deeply orange object there. And that is actually the coldest brown dwarf we know. So it popped right out of the data set and was really easy to find. The problem is, as these objects get further away, and even if they get even colder, in fact, they're a lot harder to discern. And there's one here, I don't know if you can see it in the lower left-hand, the lower right-hand image. Right in the center, there's a very, very faint orange object, which is another very cold T-dwarf or Y-dwarf there. And we have data that's been taken over many, many years now, because the spacecraft, as I said, launched in 2009, and we've been taking data all throughout the last 12 to 13 years now, actually 12 years, I guess. And we can actually use the time baseline between those data sets, since the sky is continually viewed every 6 months. And we can see whether or not there are any objects that are moving relative to the background stars. And this particular little orange dot is moving relative to the background star, so we know that it must be fairly close. So that gives us another indication that not only is it the right color, but it looks like it's close. It probably is a cold brown dwarf as well. And one thing I want to point out is that we've counted up all of the detections, all the objects we found in the WISE images, and there's almost 2 billion of them. And so far, we've only identified 52 white dwarfs. So these things are really, really hard to find. They're really rare because you can't see them very far out. But everything that we've learned about white dwarfs comes from the 52 objects that we found so far. Okay, so what we decided to do to figure out what the end of the star formation process, what the low mass products are from that process, is to look specifically at a volume limit in space. So you can think of this as you take the Milky Way galaxy and you've got the sun sitting in it, and you want to take like a melon baller that you just take like a scoop of a cantaloupe or something with, and take that melon baller and scoop out right around where the sun is, a little scoop, and then plop that down on your imaginary plane, and then count all the brown dwarfs in there, and you can figure out how frequently brown dwarfs at a certain temperature are seen in that sample, and then how frequently brown dwarfs at the next cooler temperature are found, and so forth and so on. And you can see how what the distribution frequency is, if you will, of various types of brown dwarfs in that little volume you took. So what we decided to do was take a little volume at 20 parsecs around the sun, which corresponds to about 65 light years, because we thought that ought to have enough brown dwarfs in it that we could get good statistics. And one of the things we have to do is not only count all the little orange dots that we're finding, we also have to figure out how far away they are to make sure they're within the size of our melon baller, make sure they're within 20 parsecs. So that's what we've been doing. But we were kind of constrained because one of our resources for following these up was called the Spitzer Space Telescope. And the Spitzer Space Telescope was due to be decommissioned in early 2020. And we just had a lot of this data coming in, and we were able to find proper motion objects with the WISE data starting in about 2017 or 2018. And we had just a very short time frame in which to get objects sent up to the Spitzer Space Telescope to help us follow these up. And the astronomers themselves couldn't do this alone, so we actually corralled some help from a citizen scientist project called Backyard World's Planet 9. And they helped us look through all the images and find the brown dwarf suspects that we then followed up with Spitzer. So that helped a lot. And we got this data and this project done a lot faster than we otherwise would have been able to do. So we've identified 525 brown dwarfs of types LT and Y in this melon baller scoop with 20 parsecs on a side. And this little image in the upper left just shows you how they're distributed on the sky. And as you would expect, they're randomly distributed because it's just a random collection of objects in the galaxy. And the plot in the lower right is showing you, as a function of temperature, going from hotter on the left to colder on the right, how many objects there are in that volume. So you can think of this as either a number or a number density, how frequently they're found. And you see, as you go to colder and colder objects, it seems to go up and up and up. So the colder you go, the more brown dwarfs there are, which is quite interesting. And you might actually expect this because as these objects cool, the older ones are going to have cooled more than the ones that are young. So you'd expect there to be sort of a pileup at the colder temperatures because that's where all the older ones have to end up anyway. And I think one thing I'm going to do here, maybe, guys, is stop sharing this for the moment so I can show you this movie that is not going to play otherwise, I think. So let me bring that up real fast. Okay, let me just find it here. Okay. Oh, here it is. Okay, so I'm going to start sharing again. Hopefully I'll find the right thing to share. Okay, can you see the movie?
Yep.
Yes, okay. So we're centered here on the Earth, and we're going to pull back. And what we're looking at in the background are just the familiar constellations, but we've bumped up all of the brightnesses of the brown dwarfs so they appear as those red orbs in the background. And what we'll do is slowly pull away from the solar system, and we'll back out of the 20 parsec volume to see all the objects that we found with WISE within that melon baller scoop I was talking about. So there they are. That's our collection of brown dwarfs, all shown as the little red dots. And there's a plane that shows up here just to give you perspective of when we start to twist around and look at the volume, what it looks like. And you see these stars that are further out flying by as we spin around. And then here in a second, we're going to zoom back in again and look at this sample once again. See the Milky Way appearing in the background there. So we're zooming back in, and you see that the brown dwarfs are pretty evenly distributed. They're just here, there, and everywhere. As we fly back in here, we'll eventually get back to the Earth. As we spin around, you'll see a different collection of brown dwarfs in the immediate background. Okay. Okay, so that's our collection of objects. And let me go back to final couple of slides in the presentation. Okay, so now we go here. And this is showing, again, it's the same plot I showed you in the lower right-hand part of the diagram from the previous slide, where we have our density of objects shown by the little black dots with the error bars on them. But on top of that, we have some simulations for what this distribution ought to look like if we have either a 10 Jupiter mass cutoff, which is shown in blue, 5 Jupiter mass cutoff, which is shown in green, or a 1 Jupiter mass lower mass cutoff, which is shown in red. And you see that we don't quite have the data we need to figure this out, because that last data point we have on the far right is a black dot with an up arrow, and that means we only have a lower limit on the space density there. So we think, based on our evidence, that the star formation process is creating things down to at least 5 Jupiter masses, but we actually need more objects that are that cold. And that last data point we have there is around 350 Kelvin, something like that. And 350 Kelvin is pretty darn cold, but we need to go colder than that even to figure out what the lower limit of the star formation process is as far as mass goes. So we need to find even colder objects than we're finding with WISE. Okay, so let me just show you what the immediate vicinity around the sun looks like. So the sun is shown there at the lower part of the diagram. And our next nearest neighbor is Alpha Centauri, which is a triple system composed of another G star, a K dwarf, and an M dwarf. And then the next closest star system is something called Barnard star, which is another M dwarf. The next closest system after that is something called WISE 1049 minus 5319, which is shown there in the upper right. And that is a pair of brown dwarfs. It's an L dwarf and a T dwarf. And that was discovered by WISE back in 2013. And then in the upper left is another brown dwarf. It's a Y-type brown dwarf, which is the fourth closest system to the sun. And that one's something called WISE 0855 minus 0714. And that's the coldest brown dwarf we know about. It's 250 Kelvin, which if you translate that into Fahrenheit, it's minus 10 degrees. So that's a cold, cold, cold star. And we need to find more of those if we want to figure out what the low mass limit is, because we need to see how frequently the universe is actually creating objects like that. And since we can't do this easily with WISE, we have to look to the future again. And what we're trying to do now is leverage off a planetary mission called the Near-Earth Object Surveyor, which we hope to launch in 2026, because it's looking at the right wavelengths. So it has the same right kind of alien eyes that we needed for WISE to look at these objects. And the near-Earth object surveyor is primarily looking at comets and asteroids that are coming near the Earth, but can actually see everything else in its field of view too. So it can pick up these objects quite easily, we hope. So that's where we are going, and I'll end it there for now and take some questions.
Thank you.
Yeah, thank you so much.
You're welcome.
So if anyone has questions, feel free to go ahead. Otherwise, me and Clifton have some questions to ask.
So I think the first one somebody said in chat is the data from WISE publicly available.
Yes, so there's 2 or 3 different ways to find the WISE data. So there are professional services at IPAC for the infrared science archive, where you can get images and catalog entries and things like that for the data. But you might actually be more interested in one of the other services. There's another service called Vizier and Aladdin, which is done through the CDS service from Europe, where you can pull up images from WISE and look at those and play with the images in detail. And then there's another service which one of the citizen scientists created, which I think is probably the best one of the 3 for you guys, because it's a lot of fun just to go in and play with the data sets. But it's something called WiseView, the WiseView tool. And I can send you guys a link to that if you want to use it. But you can just put in the position of any place on the sky you want to look at. You can pull up the WISE images of that piece of sky and then blink the earliest data set with the latest data set, see if you can see any objects that are varying in brightness or moving on the sky, that kind of thing. And you can stretch it in various ways. If you want to look for really dim objects, or you want to find detail in a very bright object. So yeah, there's quite a number of ways you can get to the WISE data. So I'll try to send you guys some of the links so you can poke around with it.
So I was curious, like, in your entire day, like, what do you spend your time doing? Is it a bunch of meetings, is it a bunch of coding, or a bunch of reading papers, or what do you spend for most of your day?
Yeah, most of my day, so at IPAC at Caltech, I'm employed to actually work on NASA missions. So a lot of my day is spent doing things that are related to either the data themselves and assuring that they have the right quality to be useful for whatever scientific purpose they were taken for. And that involves a lot of document writing and verification that, you know, the code that we're writing is actually doing the quality checks we need on the data. And if we're on an active mission like WISE is currently, we're looking at data that come in every day. So we're quality assuring that those data look all right and are good enough for the public to use. And you want to be on alert for anything that maybe has gone wrong with the spacecraft in the last 24 hours. If you see anything unusual, you want to be sure you spot it right away, so that you alert the team at JPL, the Jet Propulsion Lab, that, hey, we see a problem, can you check into this? And they'll check on the health of the spacecraft and make sure that everything is okay, and if not, try to correct it. And we've had a few hiccups like that in the last 12 years, but they've all been easily correctable, so that's been great. But yeah, a lot of my day otherwise is spent in meetings, and if I'm lucky, I can get an hour or 2 in there to actually do some of my own research.
So I had a question about like the new satellite, I think that you were sending, that you were hoping to send up in 2026. So how far can that see? How far like away can it see like the brown dwarfs that you're trying to find?
That's a good question. So for the brighter type, the warmer brown dwarfs, the young M dwarfs and the younger L dwarfs, it will probably easily be able to see those out to 100 parsecs or more. So we're talking 300 or 400 light years even. But for the wide dwarfs, when you get to the very cold ones, the ones like the 250 Kelvin object, the one at minus 10 degrees Fahrenheit, that one we may only be able to see out to like 12 or 15 parsecs. So at best maybe 40-ish light years, and it's just because those are so faint. Those out because there's going to be, again, billions of sources in the data sets for that mission, and we have to look for the few dozen that are actually the wide dwarfs. But it'll be fun to try to do that. Okay, other questions?
Sir, I have. The brown dwarfs, as you said, the minimum mass of it must be above 7 to 10 Jupiter masses, right?
So ask your question again because you were kind of breaking up there. I'm sorry.
Yeah, so the brown dwarfs, the minimum mass of it must be above 7 to 10 Jupiter masses, right, sir?
So I should probably explain that. So there are two different definitions that astronomers use for brown dwarfs, and I use the older one through my talk, and I probably should have explained that at the beginning. So the original definition of a brown dwarf is just anything that formed via the star formation process and didn't have the thermonuclear fusion in its core. And that could be anything that was 72 Jupiter masses on down. But in the last 15 or 20 years, there's been an alternative definition of a brown dwarf, which is they are ones that burn deuterium, which is the heavy hydrogen I mentioned. Those are the purple curves on that diagram I kept showing. And those would be the ones between 72 Jupiter masses at the top end and 13 Jupiter masses at the bottom end. And some people consider anything below 13 Jupiter masses, regardless of how it formed, to be a planet. And since I'm an old timer, I never thought of brown dwarfs in that term, so I keep using the old term. But yeah, some people would refer to anything that's lower than 13 Jupiter masses as a brown dwarf, regardless of whether it forms a planet or it formed from the star formation process. Does that answer your question?
Yes, sir. Thank you very much.
You're welcome. Okay, any other questions?
When you were in college, right? Was there any specific one topic or what made you choose research onto brown dwarfs? There's so many types of stars and so many different astronomical objects. What made you specifically choose that?
Well, when I was an undergraduate, I went to Vanderbilt University, which is in Nashville, not far from my hometown. And all the astronomers who were there worked on stars. And so I did little research projects on the side, when I was an undergraduate, on the stellar astronomy they were doing. And after I got my bachelor's degree, I went on to the University of Arizona to get my PhD. And I thought, you know what, I'm going to branch out. I'm going to do something that's sort of extragalactic or cosmology or something, because I've been working so close to the sun for so long. I want to see what it's like to work on galaxies outside the Milky Way. And I did that for a little while, and I realized I didn't like that. And the reason I didn't like that as much is that it didn't seem to me quite as precise, because you were looking so far away, you couldn't really tell whether you were finding everything or whether there were galaxies missing because they were just too faint. And it was hard to measure accurate distances to them. And after a while, it just that got annoying to me in some weird way that I can't really even explain. But I decided to go back to stars because I kind of went back to the little boy that was on the hay wagon again. I said, I really want to look at those worlds that we might be able to travel to one day. Maybe not in my lifetime, but in, future generations. And I thought, I want to settle back into the solar neighborhood and look at things that are closer to the sun. So that's essentially how it ended up. And since a lot of the new field nearby was actually brown dwarfs, since they had been theorized and hadn't been found yet, I thought, that's what I'll do. I'll see if I can be one of the first people to find some brown dwarfs. And it just happened to work out that way. Okay. Other questions? You guys had some good ones. I'm impressed.
So somebody asked in chat,
Okay.
how do elements with larger nuclei form in colder brown dwarf's atmosphere when the dwarfs can't sustain fusion reactions?
Oh, that's a great question. Yeah, so the brown dwarfs that we're looking at are primarily second and third generation objects. So there have been a couple of generations of higher mass stars that have already formed. And higher mass stars, I should mention, go through their whole life cycle much more quickly. So the more mass you have, the more quickly you burn it off, and the more quickly, if you're a very high mass star, you go boom. And boom can either be you become a black hole at some point, you become a supernova, you blow off your material and become a neutron star, that kind of thing. So that's what very massive stars do. But when they do have this explosive event, they throw out all this material that's the leftovers from their nuclear fusion process into the general, what we call the interstellar medium of the galaxy. And even if that star started out as like almost pure hydrogen, because it had fusion in the core, it was creating more massive elements as it went along. And when it goes boom, those massive elements are released into the Milky Way. And slowly, those more heavier elements will come together and they'll start to collapse and form their own new stars. And so you have new stars that'll be formed that have heavier nuclei in them, and they'll start fusing as well and form even more heavy nuclei. And what happens over time is you get a galaxy that has more and more non-hydrogen in it. So it's got more nuclei that are heavier. And the brown dwarfs are looking at primarily, like I said, are second or third generation objects. So they're out with heavier elements that aren't just hydrogen. So that's why they have those things in the atmosphere. Okay, other questions?
So last question. So is it safe to assume that the atmosphere of brown dwarf is similar to that of Jupiter, sir?
It's, well, the typical atmosphere of a brown dwarf is very similar to Jupiter in the sense that the atmospheric composition is very much the same. And we also think that as a result, they have a very similar mix of molecules. And we also think that brown dwarfs, as you probably saw in some of the artist renditions I showed, we think they actually have banded atmospheres too. So they have collections of clouds and suspended dust particles and things like that in their atmospheres that make them look very planet-like. The only difference really between, well, there's two differences between why Jupiter might look a little different from a brown dwarf is two things. One is, since Jupiter formed, we think, from the planetary formation process, you might have a different core makeup than your typical brown dwarf because it may have accreted from heavier material that started out as its little planetesimal before it accreted more material from that leftover protoplanetary disk that was around the sun itself. So there might be slight chemical composition differences, but the other difference is that Jupiter is irradiated by the sun. So there's a lot of the ultraviolet radiation that falls on the atmosphere of Jupiter that changes what some of the chemicals in the upper atmosphere of Jupiter are doing. And Jupiter, as you know, has things like aurorae and things like that in its upper atmosphere because of interruption. And your average brown dwarf probably won't have that because it doesn't have a host sun nearby that's giving that UV radiation onto it. So the atmospheres will be a little different for that reason as well.
Thank you, sir.
You're welcome.
So I kind of have like a really broad question. So what are you most excited for just in astronomy in general over the next 10 years? Like, are there any like discoveries that you hope to happen over the next 10 years or any telescopes or any like projects or missions that are going to happen over the next 10 years that you're really pumped for?
Well, there's a few things. I'll try to be brief. One is we have evidence from star formation regions that there are brown dwarfs that have formed in the star formation regions and have what appears to be a protoplanetary disk around them. So we think it's possible for brown dwarfs to have their own planets. And we have not actually observed any real brown dwarf planetary systems yet, but I think that would be kind of fun because it's like a planet with a planet around it. You know, it's like we don't even have the right words to describe that really. And I think we might be able to find some of these via transiting surveys because you will eventually see the planet coming in front of the brown dwarf if the alignment is right relative to the Earth. And there are a bunch of missions that are now looking at transiting, looking for transits around objects. So I'm hoping they'll find one that's around a brown dwarf at some point. But I would say another thing I'm looking forward to, and it may not be in the next 10 years, or it may be in the next 10 years, and that is identification of life outside the solar system. And the thing I'm not really certain about is if we haven't already found it and haven't realized what it is, because we have a very narrow definition probably of life, because we have one example, and that's what we find here on Earth, right? But it would be really neat if we see some signature of something in the atmosphere of one of these exoplanets or a brown dwarf that's like, how did that molecule get there? That can only be produced by, cows, or can only be produced by plants or whatever, because it's chlorophyll or everything. And that would be really neat if we could identify something like that and say, there's life right over there on that planet. We think there's life. And I think that would really change a lot of us as a civilization to realize that, we're really not alone, and maybe it's just, maybe it's just going to be an amoeba crawling around on the ground or something, but at least it's life in some form. And I think that would be really neat.
Is it cool if I ask another question?
I'm fine. Yeah, go ahead.
I wasn't here last meeting, so I couldn't introduce myself. I'm a high schooler from California. And is there any notable opportunities that you could, that you would recommend for someone my age? Because my options are definitely limited, right? So, Is there any advice I guess you could give me on that front?
Yes, absolutely. We've had a number of high school students who've gotten in touch with us who are, especially since everybody's homebound during the pandemic. It's like I know I'd be itching for things to do. And we had something at Caltech this summer called the Summer Research Connection, where we paired up with a bunch of local Pasadena folks to actually do projects in the summer. And I had my group actually looking for Y dwarfs in the WISE data set. And all three of the high school students I had working on that ended up on the paper I just published. So they were all co-authors. So that was a lot of fun. And I think they learned a lot just watching the astronomers interact, because we had weekly meetings on Zoom. But the funny thing is Caltech, and I don't know whether this is Caltech lawyers or what, they decided that they didn't want to do any more volunteer projects, because they're worried about how pandemic and doing things. And we found a workaround around that so that we're not violating any Caltech rules. So they said, as long as you bring in your high school students and make them part of a citizen science project, like the Backyard Worlds Planet 9 project I was talking about, it's still legal to actually mentor them and have them do projects and things like that. So that's actually what Tarun and I have been doing over the past few months, is we've just been connected with the Backyard Worlds folks. So if you want to send me through Tarun or whatever your information, I can get you connected to that group, and you can start joining our meetings, seeing what kind of research you can do if you're interested in playing around with the data sets. And we're happy to try to.
I would be honored. Okay. Is there any? Do I have to be a certain something to other? I'm sorry if this is related to the content of the meeting, but I'll DM Tarun, I think.
Yeah, we have citizen scientists from all walks of life, of all age ranges, so I'm sure you'll be just fine.
Thank you.
You're welcome.
I'm going to continue off of that question. So I heard you went to the University of Arizona to get your PhD. I currently live in Arizona, and we'll be going to NAU soon. I'm trying to find things like what you were just talking about that I can help out in the lab, or just even if I just count dots. Is there any way Arizona has the same opportunities as California does?
Yes, you don't have to be in California to do this citizen scientist work. So if you want to send me a note too through Tarun, I can get you hooked up with the Backyard Worlds people too if you want.
That sounds amazing. Thank you.
Okay, yep. Glad to help. And we're actually very, very honored to have people like you helping with us, because it takes a lot of eyes to do some of this work. And we found out that people are willing to do it, and they're really enthusiastic about doing it. And we had no idea how much we could actually give back to the community just watching how we operate. And I'll just mention one of the things that the students over the summer told me. They said, we really enjoyed joining your meetings because we saw all the astronomers sitting there arguing together. Because one of the citizen scientists would find a new object, and there'd be one group of astronomers who'd say, oh, that looks really interesting. And there'd be another group of astronomers say, oh, that's a piece of junk, blah, blah, blah. And they would hear all the back and forth, and we'd start arguing for and against. And we thought, well, maybe in some cases we'd need more follow-up data from one of the ground-based telescopes, or maybe even a space-based telescope. But eventually we'd start collecting data on each one of these candidates, and we'd find out which ones were really interesting and which ones weren't that interesting. But they said just hearing all the back and forth and learning the fact that science is not a linear process, there's all kinds of false turns and things you make as you're trying to decide what your data is actually telling you. And they said that was the funnest part for them, was just learning how the process works. And I hadn't realized that. I guess when you're in it, you don't realize what you're actually doing.
Is there
any
more questions? Yeah, because this is getting very long. So we want to make sure that we don't get like 3 or 4 hours of meeting of some sort. But this is good. It's really awesome.
Could I?
Yeah.
So, was there anything that when you were learning astronomy, right? Was there anything that specifically struck out to you as like maybe like, I don't know, some equation or some concept that was like the pinnacle of your study, like the most beautiful thing that you've seen with regards to like astronomy or physics or stuff like that? Is that
I think, I was always pretty good at math, but I was never really struck by equations in the way that some physicists are really struck by equations. They're like, oh, here's the equation that describes the entire universe. It's the theory of everything. That never really appealed to me. I was more into discovery. So I really like discovering new things. And I think it's when we started discovering the new spectral class, the very first one we discovered, which was the L-type dwarfs, and realizing that, astronomers all over the world were starting to study this thing that we didn't know anything about prior to that. That was really enjoyable to see, because it's like, I had a part to play in that, and that was a lot of fun because no one knew these objects even existed, even though they'd been theorized before that point. And here we are, we have a whole new science that people are going to go off and start studying and really branching out and doing different things with. So that's what really kind of struck me about brown dwarf science in general.
Thank you.
Mm-hmm. And I see we have another question on the chat. So let's see. The question is, how is it possible to identify if a star is a second, third, or other generation star? Do brown dwarfs tend to form as these children stars? So those are both great questions. I'll answer the second one first. So by looking at the solar neighborhood we have in this 20 parsec sample I was talking about, we're looking at objects that have formed over the lifetime of the galaxy. And we don't see any difference between the number of objects that are formed there and the densities of objects that are formed as a function of temperature than we do if we look at a very young star formation region that's forming right now. So it looks like brown dwarfs have formed equally well in the past as they are right now in new star forming regions. So we think brown dwarfs can form regardless of how much heavier elements there are in the material. So that's the answer to the second question. The answer to the first question is we can tell when we've got an older generation star by looking at how many heavy metals it actually has in it. Because as these objects get colder and colder, the kinds of molecules they can form depends upon how much of that heavier element material is actually in the atmosphere. And if you don't have a whole lot of things like titanium oxide and let's say, I'm trying to think of another element that doesn't have hydrogen in it, I'm having a hard time. Oh, carbon dioxide, for example. If it doesn't have a lot of titanium oxide and carbon dioxide, that may be because the little carbon and oxygen atoms can't find each other because they're so rare. So there's not a whole lot of CO or CO2 to be made. And you'll see primarily molecules that are made of hydrogen, like chromium hydride, water, things like that. So that's one of the ways you can identify if you have an older generation stars, that you just see lots of molecules with hydrogen and nothing else.
Sir, is there an email ID where I can contact you, sir?
An email?
Yeah,
Yeah, I can send you my email.
yeah. Thank you, sir.
I'll put it right here. Okay, so that's my Caltech email if anybody wants to write me directly.
Do we have any more questions? Well, if we are done with our questions, I would like to personally thank Dr. Kirkpatrick for spending his time and discussing with us about his career and how he came to love astronomy so much. So thank you.
You're certainly welcome.
Same as me as well. So first of all, thank you to everyone for coming. I really enjoyed it, and hopefully in the future we can have more meetings and hopefully meet more people and grow as much as we can. So thank you to everyone that came. All right then.
Thank you.
I'll see you guys soon, hopefully.
See you guys.
Bye.
So, I don't, sorry, I don't know how to pronounce your name exactly. Tarun? Is that?
Yeah. Yeah.
What's your Discord thing? I don't exactly.
I'm Flame Destruction.
Okay, cool.
Are you on that Discord?
Yeah, I'm on the board.
That's kind of a cringy username. It's from like 10 years ago, but yeah, just send me a message and I can help do whatever you may need.
All right, cool. And also, I wasn't here last time, so did I miss anything?
No, not really. It was more like administrative stuff. Oh, also before you guys go, I mean, it would be really great if you could share this with your friends. Like if your friends, wherever you are from, that are interested in space, physics, whatever, to come. Because really, our goal for the society was to just put as many people as we can together who are interested in space, and hopefully in the future we can do projects together as a team and hopefully achieve some really cool stuff.
Yeah, I want to thank everyone for coming. I do think like as we last lecture we didn't have that many people. For this one we had like around 13. I do think like we'll continue to grow as more people like come. Like hopefully you guys will come back. We'll continue to set up lectures. Our next one will probably be from the University of Minnesota, where me and Tarun are from. And we want to thank you guys again all for coming.
All right then, see you guys.
Thank you.
Bye.
See you. Bye.